I am joint between Northwestern and Argonne. The research I'll be showing you is primarily performed at the Advanced Photon Source at Argonne National Lab, and then I have also laser labs at the Center for Nanoscale Materials, which is just abutting it right here. And I'll tell you kind of a swath of some different types of research, all related to carrier dynamics, but coupled with phonon type properties and lattice dynamics in particular. And you know, it's nice to be able to go at the end of the day after Ivan and Gabrielle and Ivan have also given some important aspects of especially the electronic spectroscopy type characterizations, which we do perform as well, but mostly I'm going to be focusing on these lattice type dynamics here. So one thing that I'll be talking about quite a bit, and many of you may know this like the back of your hand, but just to make sure we're starting in kind of a similar place. So thermal motion in crystalline solids, you have phonons, which are in similarity to molecules, which maybe more of you are still familiar with. You have different types of vibrational modes that when you get those moving, they have different energies associated with them. And just in crystalline solids, because you have a periodic lattice, you do have the Brion zone, so you have momenta that are different in different directions, essentially. So, but the key feature of a typical type of phonon dispersion curve here is that you have two sort of classes of phonons. So there are acoustic modes, which are kind of compression and expansion of the whole lattice. So, most of the atoms are moving in the same direction at the same time in that sort of motion. But compressional waves, kind of like an accordion or such. And these are, even though they can be low energy, these are the ones that kind of go down here to near zero. These do distort the lattice and deform it, and that can actually have substantial energy implications with regard to the nanoparticle. And then there's the types of modes called optical modes, which are these ones of higher energy and that have less dependence on momentum. And these are really motions where the atoms are moving in opposite directions. Because of their opposite motion, if the atoms are of different types, those create dipoles. And because they have dipoles, they couple to light more readily and therefore are referred to as optical because of their dipole. So these tend to be higher energy, as you see here, and then they're also more local. They can be within a single lattice unit cell. So the key thing to think about with phonons really is that when you have a static temperature, you have a certain energy you might be thinking about of a phonon, and you can then do things like calculate how much phonon population you have for that given energy. These are bosons, meaning you can have many of them. And then you also have, you have to remember that when we start to do anything like photoexcite systems, photons typically that we'll be using are, say, in the visible wavelength range, which are 1 to 3 electron volts, for instance. And that's much higher energy than these phonons. So one optical excitation in many cases can create more than one phonon also. And there are some arguments about, in certain cases you might couple to optical phonons from electrons, and in other cases you might couple to acoustic modes. And if you have optical modes, they also do couple with things like acoustic modes to create populations of lower and lower energy over time. Okay, so what I'm going to try to argue to you a little bit is that phonons are really quite important in nanoparticle systems. And many cases, I think people kind of have a view of nanoparticles as being frozen solids, where their lattice is just fixed. You think of what's the energy landscape for that fixed set of atoms, but you do have to remember that they're in motion. And so phonons are going to be important for them. And the most readily available way to think about phonons being important to nanoparticles is thermal conductivity, which is not a non-equilibrium concept, but it's just, as you have phonons, vibrational energy in, say, this core particle here, and this is some picture from John Mallon's work together with Dimitri Talipin, you can think about how can phonons migrate through these heterogeneous types of systems, and that impacts what their total thermal conductivity is. But also with regard to electrical carriers and charges, they play important roles. And so these are pretty varied. So they can affect the band gap energy directly. And in one way of thinking about that is just as you scan temperature of a system of nanoparticles, you will see things like their band gap migrate in some cases to higher energy or lower energy, depending on the details of the electronic structure. But generally the lattice will be expanding as it gets hotter. And so that can change where the band gap itself is because the average bond length is changing, and that changes what the potential that the electrons and holes are seeing in the lattice. Changes transition line widths. So you may have already been seeing some of the data where people go to low temperatures and you see narrower line widths, and that's as you have less and less phonon involvement in the transitions, they become narrower. But also phonons are just involved with if you have a 2 electron volt material and you photo excite it with a 3 electron volt photon, the carriers that you initially created are going to cool to the band gap, and that's going to create phonons directly in that regard. And how quickly you can generate phonons affects how long these carriers can be hot. If you could control electron-phonon coupling, you could design materials perhaps where the electrons stay hot for longer periods of time, which translates into higher voltage and higher redox potentials. So there's a lot of interest in trying to do that if possible. And then there's kind of more complex ideas in some regard of things like what you'd call transient disorder. So while phonons are present, your lattice may look different in a non-equilibrium sense relative to what it does for the temperature that you are kind of suspecting the system is at based on static temperature. So you can have the material launch a disordered mode of the lattice for a short period of time, and that itself may change things like transition strengths and lifetimes. And so these can be important in just the actual observed behavior, especially in applications where you might have some form of time resolution. So something like a pulsed excitation, for instance. And so, and you know, I maybe don't have to argue to this crowd too much that nanoparticles are really important for real technologies. You know, solid state lighting is a key application of nanoparticles, where one of the limiting factors at the moment, you know that you can buy nanoparticles in displays, but to move them into things more like solid state lighting, these become thermally limited applications in many cases. And so how fast can you get heat out of the system? You know, what are the impacts if the system is at high temperature? Can it just keep radiating happily even though it's hot? With nanoparticle lasers, these are systems where, you know, one of the thoughts is always how long can you maintain a population inversion, but it's also, you know, you can't just pump them infinitely hard because for long periods of time, because their temperatures will rise and the materials themselves can degrade rapidly. But are there ways to make them more and more robust to elevated temperature or keep their electronic transitions behaving how you might want them to? And even in solar cells, especially if you start to concentrate light, thermal mediation of the material is important again. And, you know, are your carriers going to charge separate as you might like them to, or are they going to start to have other structures present that are not the material that you designed into the solar cell to begin with? Okay, so just talking about carriers and creating phonons, in some cases, even when you might think of an application as being DC, you know, where it's just a constantly on device, you, in many cases, have non-equilibrium phonon creation just from the fact that a photon is absorbed at some instant in time, even in a solar cell, but then your carriers may initially be up at high energy, but those electrons are going to fall down to say the conduction band minimum. A hole, which is the absence of an electron, is going to move up into the valence band maximum. And so anytime you absorb photon energy that is in excess of the band gap, you create thermal energy. And very similar perspective is from something like an LED, where you're just injecting charges from electrodes, but you have to use overpotentials to get the charges in the first place. And so you still will create phonon energy in that case. So, but more mechanistically, you can kind of break down forms of thermal energy creation from carriers being present in 2 classes. So one of those is Intraband relaxation, which has been looked at for a very long time in nanoparticles. You know, going back to dates prior to these references, even there are arguments that electrons might be able to live up in higher energy states than the conduction band maximum or conduction state maximum, because there's this gap in energy where these energy gaps may be larger than the band gap, than what are available phonon energies in the system. And so your electron can't just fall down by emitting 1 phonon to get to the band edge. It may have to emit 5 phonons or something like this. And so those processes involving lots of carriers simultaneously could in principle be inefficient. So you might have long-lived hot carriers. But instead, what's observed in just about any measured system is about 1 picosecond relaxation to the band edge of, say, the electron here falling down. A hole is undergoing intraband relaxation in this picture also, where it's moving to the valence band maximum by letting an electron above it fall into the state below it. Okay, so intraband relaxation is very, very fast. In applications where you start to have more than one electron hole pair, and I'll focus a lot on materials that can show gain and lasing, you want to get things like population inversions. And so you have two electron hole pairs in this system here. And these represent a population inversion, which is desirable, but they can also undergo this process that my former postdoc advisor, Klimov, found, where these become short-lived, 10 to 100 picoseconds, depending on the volume of the particle. And then you go back to a single electron hole pair state by non-radiative relaxation of the one electron hole pair. So your energy is maintained here, but now you have a hot carrier, just like in the intraband relaxation picture. And then in 1 picosecond, once you form that state, you go back to a cold single electron hole pair. So both of these processes can be operative, and both are understood to create your phonons. Okay, but some of the challenge, there's many challenges, I think, in this area. So first off, when I say that you just start creating phonons, I can't immediately tell you create 6 of this kind of phonon, 2 of that kind of phonon, what the initial distribution, say, looks like. And some of that is because we don't have great tools to just read those things out. Instead, what we're sort of left with are observables. These are just some observables from my lab, where we can implicate phonons, and we might be able to make strong arguments for their existence, but we're not directly observing them. So in one case here in the top left, these are just regular Ked Sonic Nanoparticles in an alkane solid matrix. And if you cool them down very cold and photoexcite them, you see fast emission at early time, is shown here by a time-resolved emission scan with time on the x-axis and wavelength on the y-axis. And you see you're getting emission that's rapid at early times, and then it gets slower later. But this window of time is pretty small, so you're not really having a population change during this time. What you're kind of seeing is more of the instantaneous radiative rate being higher at earlier time and slower at later time. And that said, in nanoparticles, it's understood that you form the lower energy triplet state quite rapidly at low temperature, and that this fast emission is due to the fact that you have phonons present, and the phonons can help you radiate efficiently from this triplet state, even though normally that would be a spin-forbidden process that is slow, which you're observing more here after the phonons have flown out of the system. And this is a picture that we first put that forward in 2011, and many experiments that we do buttress this argument, and we think that it's in fact correct, but we can't directly see the phonons. In another case, this is with butyl ammonium perovskite materials that are 2D. You can create excitations in such a way that you launch a phonon of a certain energy, essentially through a difference frequency of a pump beam. And you can clearly see that there's a phonon present, and you can clearly see in this transient absorption type measurement that it's wreaking havoc with the band gap of the material, right? You're getting it to shift red and shift blue and shift red and shift blue. So it's definitely a phonon mode that, by rearranging the atoms in the system, you're causing the band gap to have changes that are at least measurable. That said, that doesn't guarantee that's the only phonon in the system. But it is indicating that one of the phonons in the system that's well defined is having this electronic coupling that's present. Okay. In still other studies involving time-resolved emission, this is with bulk perovskite materials, we can see these fast relaxation processes that occur fast radiative rates of electron hole pairs in methyl ammonium lead iodide if you excite further to the blue, whereas if you excite further to the red, possibly creating less phonons, you see slower emission. And this is a picture also that we see come up again and again in different types of excitations that we do, where we think this has a lot to do with distributions of what types of phonons are present in the organic component versus in the inorganic component of those types of systems. So, and I offer this just as something to hopefully get you thinking about, electron hole pairs are critical for the electronic function of materials, but phonons do play roles in how those electron hole pairs are recombining and going forward with your optoelectronic process. So one of the challenges is we don't have great ways to look at them. So phonons are often suggested. We might partially detect them. We can see one of them or something, like one mode that's important. But generally, we can't control it. We can't say, in this study, we're going to put in 5 phonons. In this study, we're going to put in this type of phonon. And in some cases, it can be really tricky to even make a strong argument that you have a phonon that's doing something that's important optoelectronically. So I personally see that as it's an important aspect of trying to understand how nanoparticles and related 2D semiconductor materials are responding. Okay, and so there's kind of general classes of questions, and there's more certainly that could be asked. But when you make an electronic excitation, such as with an electron hole pair creation from a photon absorption, you could say, how fast are you creating phonons? Which phonons are you generating? I showed you that there's different types of modes that are present. In some systems, the modes are more complex than what I showed you. How fast do phonons evolve between those different modes? How fast do they move through interfaces? And then what electronic impacts do they have? So, if I tell you you have an acoustic phonon in your system, is that something that's going to be dominant for the behavior of the system electronically, or is it going to be something that's not too relevant? Okay, so I'll tell you a couple of classes of stories related to this. Most of what I'm going to tell you about is involving transient X-ray diffraction. And I know from the earlier talks, there was more covered with optical spectroscopies. So I'll spend a little bit of time trying to do some basics about relate some basics about X-ray diffraction types of studies. But I'll tell you a little bit about what goes on in these transient X-ray experiments and why we started to perform them. And we've looked at a number of different systems at this point and still continue to. I'll tell you about a couple of optical means that really kind of take synchrotron-based experiments that are less accessible to optical experiments where we can kind of do some additional fine probing. And then I'll tell you also about some approaches that get more at these interfacial types of processes of, if your nanoparticle core was hot, how long does it take it to get, say, the ligands to be heated? Or in the case that I'll show you, it's more of the vice versa. Okay, so my initial motivation for getting into this area, which goes back something like 8 years, stems from the important work of Victor Klimov with doing things like gain and lasing in nanoparticles, where you can photoexcite at a film of nanoparticles of Ked Sonic in this case, and as you excite harder and harder, and these excitations follow Poisson distributions, which have been discussed earlier today. As you excite with more and more intensity, you create more and more electron hole pairs, and you go from having a fluorescent spectrum at low power to getting these narrowed and superlinearly growing stimulated emission bands, which you can use to turn into lasers and such. And so that development is important for the field for trying to achieve these localized light sources that can be compact. But then, so what was motivating me to try to get into some of these understandings of phonons is a subsequent observable that was also shown, where if you look at optical gain, and I won't maybe get into this axis too much, but the idea here is that as you cross this value of 1, when you're putting a pump beam in and then probing at the transition energy of the conduction band, valence band gap, you start to see more light output come out relative to the probe light that you sent in intensity. And so that means you're getting optical amplification. And so, you want to just see this as you pump the system harder and harder, which is this x-axis, number of electron hole pairs on average created. You'd expect that as you keep pumping harder, you might get more and more gain, or it might saturate as you start to fill up the band edge states, because you have things like Fermi's rule saying you can only have so many spins at the band edge. So, but instead of that saturating fully, what happens in zero-dimensional nanocrystals is that gain starts to decrease, and it can decrease pretty slowly, like what's shown here for the largest nanoparticle. But as you go smaller and smaller, you see that this is pretty important effect that was going across the different systems. And as you go to really small particles, you actually never achieve gain, and instead this turnover of gain to decreasing is at smaller and smaller powers. And so some of the thought there was that maybe phonons in these smaller systems dominate the electronic structure more and more. You have fewer atoms that are easier to cause expansion and contortion of the lattice. And so therefore maybe the electronic structure is getting botched in some way that is not desirable. Okay. So, and there's reason to be worried about the lattice, essentially. And so going back into the 90s, Alvasados's group, and this is understood just from thermodynamics as well, but they were showing that in electron microscopy, if you took something like Ked sulfide nanoparticles and made them smaller and smaller and watched electron diffraction in a TEM, you could see that as the particles get smaller, the melting point of them also gets depressed. And so whereas the bulk system is up here at 1700 Kelvin, really small nanoparticles, this is at 600 Kelvin or thereabouts. And so, so this is something that I said is thermodynamic. It's that as you have fewer and fewer bonds holding your crystal together and the lattice enthalpy related to those internal bonds, you replace that with small nanoparticles, you lose that lattice enthalpy and start to have all this surface energy you're creating. And surface energy is bad. It raises the energy of the system. And you can think of it as if you go to a small enough nanoparticle, you pretty much are getting back to starting materials of what you were forming thermodynamically as a large crystal. So smaller and smaller nanoparticles, that effective surface energy causes the band gap, causes the melting point to be depressed. So what we set about doing were transient X-ray diffraction experiments. And we started doing this in about 2011 or 2012. And a couple of different manifestations where there was a number of failures, but it started to hit the pavement and work and has progressed appreciably. So, and I'll get into the basics of this in a second, but just so that you know where we're going. What we did in this experiment, it's like transient absorption, where you have a pulsed laser. We use femtosecond or picosecond lasers that are pulsed here, say at 400 nanometers. That's going to hit a sample. These samples we typically use in the form of a flowing jet, although in some cases we can use solids. So we have a flowing jet that helps us get renewed material. And then we take the synchrotron, which is a 6 megahertz source of X-ray pulses that in different modes of operation can be a lower rep rate, but also we can do things like gate detection of it. We take an X-ray pulse and have a time delay between the pump pulse and the X-ray pulse. And they both cross the sample in the same location. And then the X-rays go through the sample, and I'm going to tell you about how they diffract and create these what look like ring structures out here. And then we average what the signals look like there for a long time at one delay, then we change the delay, make more measurements and so forth, and can build up something that looks like transient absorption, but it's X-ray diffraction as a function of pump probe time delay. And we can change the pump fluence, and we can change the nanoparticle sample and so forth. Okay, so just a little bit of a step back, and I hope this is not too far of a step back, but I know more people in this audience are optical rather than thinking necessarily about structure. But if you take a step all the way back just quickly to Miller indices, you can think of, if you just have a nice periodic unit cell or lattice here, you have some easily defined vectors that are your unit cells, or your unit vectors of A and B. And so, so if you start saying like, oh, I'm going to take 4 steps over here to the right and then 2 steps down, I can define this ray here, which is going from 4 to -2. And I'm starting to define planes in my crystal. And I can look around at these identical unit sites, the lattice sites, and draw a bunch of parallel planes that are present that are all the same. So from those planes, we're looking at across a couple of these planes here, you have what's called Bragg diffraction. And Bragg diffraction is conceptually pretty straightforward, but it's just that you have X-rays coming in. This does happen with optical light also, with what are called Bragg mirrors, so Bragg reflectors. So you have an X-ray come in, and these two are in phase with each other. This X-ray comes down and hits this lattice site. And when an X-ray, which is still a photon, hits an atom of material, really what's going to happen is the X-ray disappears and polarizes the electrons in the atom, but then it re-radiates them. And it might say, try to re-radiate in this direction. So now X-ray 2 comes in, and it's going to penetrate further down. It's going to hit another unit cell site, and then it has some chance of also radiating out in that same direction. But now there's a question of, when it comes out, is it going to be mating up in phase again with the X-ray from the first unit, the first lattice site, or is it going to be out of phase? And so, so Bragg criterion really is just saying, well, if you're at some angle, and the angle here is just going to get you trigonometry to say, how long was this path difference for when these two had this exact same phase relationship. This difference here that's present, going from A to B to B to C, has to come out again in phase, a multiple of the wavelength down here. so that you emerge with the same phase front and then have constructive interference. And so because your X-rays have a certain wavelength, and it's convenient that these wavelengths are comparable to the lattice planes in crystal and solids, that helps you get measurable diffraction intensity. So your X-rays that came in one direction are going to be observed going out of the sample in a different direction, both defined by theta for entry and exit. So when you hit that criterion, you get diffraction peaks. If you're off axis, like if you're not sitting at the right theta here, you just don't emerge with the same phase relationship, and an intensity of X-rays at this other angle is not going to be observed. Okay, so just one other relationship that's valuable in X-ray diffraction is a lot of times we talk about Q space, which is inverse space. And really this is just related to 2 pi over d. So d being the separation of your planes in a given Miller indexed plane set. So this is, large Q values relate to small d values. So it's like spatial frequency is a way to think of it. So a large Q value means you're talking about really small distances. Low Q values mean you're talking about really large distances. And so we like to measure over a range of Q values so that we're sensitive to planes that are at different distances within that measurable window. Okay, and this is just a little picture from an applet that's somewhat useful for looking at this phase relationship aspect, just to understand the diffraction a little more. Okay. One last bit about X-ray diffraction in just the broad brush is that there's different symmetries of solids that are possible, and X-ray diffraction itself is used in the non-time resolved sense to just try to do things like identify what phases are present. Sometimes when you work with people that do X-ray diffraction a lot, you'll notice they can look at an X-ray diffraction pattern and pretty quickly tell you, oh, that's a high symmetry phase or that's a low symmetry phase. And just a little bit about that is that if you have something like, say, a perfect cubic unit cell here, there are fewer distances that are involved in that perfect cube because you have all these different lengths being identical. So when you measure diffraction, there are different planes in this real space image, but in Q space, they have the exact same separation. And so all lead to the exact same reflected angle. So you see fewer peaks for a cubic cell. If you start to distort your cubic structure in essentially any way, that starts to lead you to have more peaks. So if you go to more of like a rectangular prism, you start to get multiple reflections because now your planes are at slightly different distances when you look at different orientations of the crystal. And if you keep decreasing that symmetry, you get more and more features. So if you see few peaks in X-ray diffraction, that suggests high symmetry. And if you see a lot of peaks, it suggests low symmetry. Of course, this is always, when you're measuring it, it always matters that it's a pure material as compared to like a mixture of 5 things or something like that. It's also true you can rely quite a lot on databases that exist where essentially you can look up what angles you're measuring, what Q values those relate to, and then what possible structures are present. Okay, so and just a little bit more detail about nanoparticles in particular. When you're talking about X-ray diffraction, usually you think about a perfect unit, a perfect lattice that repeats on forever. But X-ray diffraction of nanoparticles has a couple of issues. One is that if you start to have particles that are smaller than 100 nanometers, relative to diffraction, that starts to not look like it's infinitely large. And so what happens is your diffraction peaks start to broaden. And so there's a paper from Alvasados, Brazilian folks, or was the first author, showing that as you go from pretty big particles to really, really small particles, you can see that the widths of these X-ray diffraction peaks becomes really broad. And there's something called Schaller broadening, which is just relating that you expect these widths to increase. And you can kind of think of it as the Fourier transform of the physical extent of the crystal. If it goes on forever, you get one exact frequency. If your lattice doesn't go on forever in space, when you Fourier transform, you get something that's broader because it's less well defined. So that's useful in a way also because it's a way to size your nanoparticles as well. So if all your peaks are kind of similar width, it suggests that they have a size that can be evaluated by the Schaller equation. Okay. It's also true With nanoparticles as compared to single crystals, instead of getting specific angles that are just defined in like, you know, seeing individual spots on a screen, right now you're looking down the axis of the X-ray coming to the sample. Instead of seeing individual spots, you see rings. And that's because you don't really have one sample in the beam. You have billions of samples of little tiny nanocrystals with every orientation possible. So if you had one crystal, you might see individual spots relating to those different planes and the exact geometry of the X-rays relative to your exact crystal. But because you have all of them, you have all these different rings. So that adds a little bit to the complexity of data manipulations. Just you have to do things like circularly integrate this. You have to you know, always worry about things like backgrounds from substrates that might also be scattering and such. Okay. Furthermore, if you want to do anything time resolved with X-rays, you have to have a pulse source, and that's where synchrotrons are useful, free electron lasers are useful. There's benefits and detriments of both types of sources. Okay, so getting to some form of data, here what I'm showing you is just one of our first successes, essentially, where dashed here is what the X-ray diffraction pattern looks like for this range of Q values corresponding to these different Miller indexed planes of Ked Sonic Nanoplatelets. And the dash is static. And then when we come in and photo excite the system, you see that the red trace comes in and the X-ray diffraction has gotten a little bit weaker. And so this is something that with knowing things like transient absorption, where you see small changes in a probe beam relative to a pump, you can come in and do things like just difference them to look now at delta scattering, change in scattering. And then this is something then that we can look at for a given pump probe time delay. And then here we're scanning through pump power that's present for that fixed time delay. So, so a couple of observables. One is that there's these black lines that right now are going through the center of these X-ray diffraction peaks for the static case. And if we calculate the difference and show those same black lines, you see that the differences don't just match up exactly with where the black lines are. It's a little bit off of that, which makes you wonder if you're doing something wrong, but I'll tell you it's not. And then you also have these little lumps that are off to one side. So first off, just how can we understand what this sort of data looks like? And so again, taking a little bit of a step back, if this blue trace here is what your initial Schaller broadened X-ray diffraction peak looks like, you can imagine a case where now you just heat the crystal up. That makes some phonons, they expand. So your spatial frequency decreases, so Q decreases, but it's still a crystal. So now your diffraction peak moves to where the dashed red line is here. So that's just a picture of it still being crystalline, but being heated. And if you difference those two, you'll get a derivative type of line shape, right? So it should cross zero, roughly where these two intersect right here. You'll get a negative lobe where you used to have diffraction intensity that you lost, and you gain intensity where your diffraction now moved to. So that's one scenario. A second scenario is that you don't just heat the crystal. Maybe you heat it or heat some number of the nanoparticles in the sample, but also you're disordering some of them. And so instead of just having this picture of a heated nanocrystal, if you disorder your crystal, you start to lose the possibility of having Bragg diffraction because you don't have a crystal. You need to be able to have well-defined phase relationships to see these interference peaks at all. So now you shifted to, or your heated component wants to show a derivative, but there's some other population as well that is just loss of this blue peak. So if you just subtract off some of this blue peak before you difference it, what you get are these red types of line shapes where there's a positive little lobe at low Q. There's a dip, but notice it's not at the center of the static peak anymore either. That's influenced because of the fact that there's a derivative present as well. So that shifts it to higher Q in the negative component. And if you look back at the data again, you see that actually looks quite a lot like what we're seeing here. So you'll notice at lower powers where you might only have, say, heating, but your crystals can stand it. If you look at the kind of dark blue trace here, you see what looks like just kind of a nice little derivative. And it's as you hit these systems harder and harder, you get that derivative shape to be overcome by a negative going Gaussian, or line shapes exactly are void, but they are kind of quasi-Gaussian. So one other note here is that in terms of data processing, a couple different things we can do. One is that if you take your difference data, if you integrate it and you have a derivative, you should get 0 because you still have the same amount of diffraction intensity. You're integrating a positive and a negative, so it should approach 0 when you do that. If you have something that is showing some disorder, if you integrate over this, you'll get negative signals. So sometimes we look at peak positions and heights, and sometimes we look at integrated signals as well. Okay, so bits of data that are for Ked Sonic nanoparticles, which are in some regards kind of the vanilla flavored experiment of what can we see. So in these systems, we photoexcite them, we calculate the differences, and then we can look at the change of scattering. This is now integrating, and we can, so we're seeing a recovery time scale, not just seeing at early time scanning power, but if you look now at later and later times, you can see eventually our transient diffraction is recovering. And if you hit the system appreciably harder, 20, 30 times harder, you see that there's a slight slowdown of recovery, but it still recovers pretty rapidly, almost the exact same. If you look at different crystal directions, it looks the same in terms of the recovery. So that's telling you that you're getting a homogeneous response of the nanoparticle. There's not like some unique direction in the system that is dominant. And if you look at small, medium, and big particles, you see small ones recover the quickest, and bigger ones recover more and more slowly. If you look at the total scattering, the changes that we can create, it's also true with scanning fluence. We can go to really low powers. We don't have infinite signal to noise with this method, so we can't see anything if we go to or we don't see differences that are appreciable at really low powers. If you start integrating these signals and go up and up in fluence, what you see is that the smallest particles melt for or start to show disorder. Deal with the word melt later. You see some loss of diffraction that's coming on as you have increases in fluence, and this occurs for earlier or lower amounts of electron hole pairs per nanoparticle for the smallest particles, and it goes up and up as you go to bigger particles. So larger particles, you have to make more electron hole pairs to get some kind of disordering. But if we try to call through different criteria what we think is a position where this is getting disordered, we see that those data points correlate really well with in gain and lasing measurements where you have loss of gain, or where that gain was turning over from that initial motivation slide, which is suggestive that this disordering effect is something that can really be impactful for gain and lasing. This also has the connotation, or I think is the likely causality of core shell particles lays better than core only particles, not necessarily because of electron hole pairs being more happy in a core shell particle, which certainly they are, but it's also that you're making the crystal itself more stable against disordering by making it effectively larger, making its melting point effectively higher. And so that's one of the things that helps you prolong gain and get better performance from core shell particles rather than core only. So there's this question of, if you start to disorder your lattice, as shown by having a loss of total amount of diffraction intensity, what does that mean? And I don't want to say much about theory because I'm not central to this type of calculation. But there's, if you do something like try to calculate density of states for considering what the band gap is for a crystalline Ked Sonic nanoparticle, but then you heat it up very hot using AIMD methods, where you then you essentially heat the system up, freeze the atoms in place at that point, and then recalculate the electronic structure. What you see is that the band gap becomes much smaller for disordered lattice, and this exact temperature is kind of meaningless. It's simulation type temperatures. But what you're seeing is the band gap gets much smaller, and it in fact gets smaller more quickly than what you expect just from things like thermal expansion and contraction from a Varigny relationship. So remember, your electronic structure cares about what the average lattice distances are in your nanoparticle, and as your crystals expand, you expect your band gap to change. And what these calculations are saying is that if you do in fact get disordering, you get this more steep drop of the band gap versus that temperature elevation. Okay, so that's suggestive that could further wreck gain and lasing, because when you have gain, your population inversion is occurring for a transition energy that's bridging this energy gap here. And if suddenly the material starts to absorb at those wavelengths because it now has strong allowed transitions right there as well. That's something that can compete with your gain processes effectively by reabsorbing or also wrecking what does the band gap look like while you're trying to have lasing from that state. Okay. So some other optical methods that we've used to look at this exact same problem that are a little bit more accessible are transient absorption using multiple pump pulses. So there's a little bit of an aside, and I'll get back into X-ray diffraction. But in the top left here is data shown for Ked Sonic nanoparticles, where the probe wavelength is shown on the y-axis, time is on the x-axis. And as you photoexcite this system, you see this blue band, which is bleaching of the band gap state. You have some induced absorptions at higher energies. But if you go up in power by a factor of like 400, so now you're making lots of electron hole pairs. So before we were at 0.3, which means you're exciting 1 in 3 nanoparticles with 1 exciton, very, very few with more than that, versus 100 electron hole pairs on average. This 100 electron hole pair on average data still has this really dominant bleach feature right here. And then it has these new induced absorptions that they're not 100% in your face relative to the low power data. It still looks kind of comparable. So the first question is, does this bleach that's present mean that you still have a happy band gap right there? It's the same as when you had low excitation intensities and so forth. So to set out to understand what the origin of that is, you can go to a measurement where you get into two pump beams. And the rationale to do this really is that you want to have a photo excitation of your cuvette that is not chopped, and it's at a fluence that is controlled just to make neighborhood of 2 electron hole pairs. So you have this twofold degenerate band gap, and you kind of want to study the nanocrystals when they already have that full of excitons. And the reason for that is that band edge bleach is strong, and even when you hit the system really, really hard, that one transition disappearing was a strong absorber before, so you can still see it in the differences. That's quite observable. So what we do in this experiment is we come in with a pump 1, photoexcite the sample. So now we have a cuvette of excited nanoparticles with like 2 electron hole pairs. We come in with a second pump beam that's chopped, which means we're going to be sensitive to differences created in the optical signals when it's present or not present, and then have our probe beam come through. And so in this upper data set, this is a whole bunch of fluences at late time where you see tons of bleaching from this band edge state. And in the 2-pump experiment, where we have pumped it just hard enough to make 2 electron hole pairs, you can see that you lose that bleach feature almost fully. And we have trouble getting rid of it 100%, pretty much just because of the Poisson distribution saying you don't always have just 2 electron hole pairs. If you get to fluences where that happens mostly, you still have some unexcited nanoparticles even. So we can largely suppress it at least, which suggests that does just come from that band edge bleach. But then when you start photoexciting the system harder and harder, what you see happen is that instead these induced absorptions that you can see for sure in one pump experiments, but are a little bit harder to interpret, they come in quite strongly and very apparently. And this, what I'll argue is that this is the absorption spectrum of that disordered material. So whether or not we call it melted, you have a lot of phonons present in the system. The lattice does not look sufficiently crystalline to diffract X-rays. And so therefore, while that's in that state, you have this electronic transition set that is to the red of where the bleach feature originally was. And this is a long-lived state. This is present for, these are measurements done at 150 picoseconds. So that's after you've had Auger recombination processes of all these electron hole pairs annihilating each other. And now you just, in principle, just have 1 electron hole pair present anymore. Okay, so the reason that's valuable, or you might wonder why we're doing that when we can do the X-ray experiment. The reason that's valuable is that the synchrotron experiments are necessarily lower signal to noise. There's more restrictions on how much experimentation we can do there. and doing experiments at really low fluence is hard because of those limited signal to noises in particular. So with being able to do this on a tabletop femtosecond laser system, we can do this with a whole bunch of different fluences down to really, really low powers. And if we just look at that induced absorption that's out in the red, that'll argue is an optical signature of disordering. If we look at the intensity of that induced absorption coming up, we see data points like this, where small, medium, large particles follow these really clear trends. And I'll note that at for the largest nanoparticles, you have to be up at tens of electron hole pairs to start to see these signals. Whereas if you were thinking that might be from something like ionizations and getting unusual optical signals from that, you'd expect it to start coming in still at much lower fluences rather than up to 10, 20, 30 excitons. So we don't think it's from ionization. And then moreover, if you now take these data that look different with particle size here and normalize them to the volume of the nanoparticles, you see that you get this nice universal trend, which is actually not something we really expect. And I say we don't really expect that because this universal trend is suggesting that when you have a certain density of electron hole pairs per unit volume, or a certain number of electron hole pairs per unit volume, or density, you have the same induced absorption signals coming in. They're at different wavelengths, but the same red type of induced absorption signals coming in. It actually matches the X-ray experiment as well, which are diamond points here. And we generically would expect from thermodynamics, because I said that the melting point gets lower for smaller nanoparticles, you wouldn't expect them all to necessarily fall on top of each other. So that the fact that they do overlap is something that's suggestive of this being a non-equilibrium phenomenon, that it's just you're seeing lots of these crystalline lattices, but it's not truly a phase transition in that sense, because that you expect to be taking place at lower fluence or lower ultimate temperatures of the lattice, whereas when they have the same density of excitations, you expect about the same temperature. Moreover, another thing that we can see from these two pump experiments is higher time resolution. And of course, with X-rays, you can do things like FEL experiments, free electron lasers, that are femtosecond types of timescales. The experiments are a bit painful though, and again, time is restricted and signal to noise is low for unless you're up at higher fluences typically. So here we can do these at controlled fluences, high time resolution, and if we look for that induced absorption signal to form, you see that it actually cares about what size the nanoparticle is. So the smallest nanoparticles, seeing this induced red absorption, comes in faster, and it takes longer and longer for bigger particles. And something that's consistent with is that Auger recombination process. So this is definitely not bi-exciton Auger recombination. It's multi-exciton Auger annihilation, but it does become slower as you go scaling with volume. And so this is something that is taking longer and longer as the particles get bigger, suggesting that you're waiting for this electronic reservoir of energy to be converted into thermal to see all this disordering come in. Check how I'm doing on time. I'm actually a little bit behind. So I'll try to go a little bit quicker with some of these other examples. With other materials like cesium lead bromide, which is another example of something where you get gain in lasing. So that's been studied a fair bit. These materials at room temperature as nanocrystals are orthorhombic crystals. It's a lower symmetry. So orthorhombic crystal structure, you see more peaks in diffraction as compared to higher symmetry phase, say of cubic. You have very few peaks, and that should be something obvious to you because we talked about rag diffraction, and you have fewer planes that are present, so you have fewer peaks. So the nanoparticles are definitely orthorhombic, shown in the black here, because they have these weak little features related to the orthorhombic phase. And in studies of these, when we've done transient X-ray diffraction on them, one thing that we didn't really set out to see but saw is, so first off, at a peak that is present in both phases. So some of these features are essentially conserved for different crystal phases, and that's because these octahedra look about the same for the different crystal phases themselves. So those octahedral type of reflections, you just see beautiful derivatives, right? Like positive, negative lobes are very, very similar to each other. But if you go out and look at some of these weaker orthorhombic features, they don't actually look like derivatives. They just look like negative going diffraction peaks in the difference X-ray diffraction. And so what that suggests, or is directly indicative of, is that your crystal is no longer orthorhombic when you do this excitation intensity. What you're seeing is cubic material, and you've lost your orthorhombic components to it. So this is something suggesting that we're not just seeing disordering. The material is still very crystalline, which is why you have these nice derivative type features over here. These guys are not very asymmetric. So we're not just disordering everything. What you're doing is driving the system optically from one crystal phase to another. And this is relevant because the material shows gain in lasing. And what it can be suggestive of is that you're actually getting lasing from a phase that is not the one that you're pumping. Your material itself is undergoing phase transitions that there may be lasing from. So this is something we studied in more detail. We've essentially evolved in what we can do with these experiments. We can do static X-ray diffraction versus temperature, watch very carefully how these lattice positions change as we're going through different temperatures. And that's that thermal expansion, just seeing static creation of mostly optical or mostly acoustic phonons. And then when we do our optical experiments, we can watch the system go through this transiently cubic phase by looking at the integration of features related to that to seeing cubic form. And then over time, we see it recover, and it eventually recovers back into orthorhombic. And that's taking something like a couple hundred or a couple of nanoseconds to fully recover. Okay. And from knowing what these the changes in X-ray diffraction peaks of especially the octahedral types of features look like, this is something where we can start to read out what's an effective lattice temperature because our derivatives relate ultimately to the shifting of these diffractive peaks. Okay, I'm going to skip this just in the interest of time. We can hit it hard enough to get disordering, which may not be too unexpected. It's also true you start to see damage of the material appreciably at higher fluences. I'm trying to make a decision because I only have 8 minutes or so. I'll tell you quickly about 2D nanoplatelets of Ked Sonic.
More time, don't worry, Richard. Just don't be too concerned about time.
Okay, sure. Okay, so so I'll tell you a little bit about Ked Sonic nanoplatelets that have already been discussed in this conference. They're really intriguing materials. Initially discovered by Sandrine Athuria and Benoit Dupertret. Sandrine actually came to Chicago and was a joint postdoc with myself and Dimitri Talipin. So we did a fair bit of work on these systems at that time as well. So these materials are remarkable in that they have very strong narrow transitions, that they're ultimately narrower than 0D nanoparticles of the same composition. And that's because their thickness is very precisely controlled. The material planes that are the large flat lattices like to be exactly one thickness and not a series of different thicknesses for the same particle. And you can make ensembles of these where you just have that one phase, or just have that one thickness of platelet. And as you step up in thickness, you can get to these different band gaps. Iwan showing that you can step this up still redder than what I'm showing you here too. So these materials are exciting also because they show excellent gain and lasing characteristics. They show comparatively slower Auger recombination, as shown by at higher fluences seeing this fast component of optical signal get longer lived, and that's the amplitude of this signal is essentially a readout of electron hole pair population. The more electron hole pairs you have, the stronger this bleach feature was, and as time goes on, you see it diminishing and eventually recovering at late times where these can overlap, as you just have one electron hole pair per particle. So this is relating Auger recombination time scale when you difference it relative to really low fluence where you never had multiple electron hole pairs. So longer Auger recombination lifetimes, and Victor may talk about this tomorrow also, longer Auger recombination lifetimes are kind of everything if you're going to try to get to something like an electrically pumped laser. So it's also the case, so we can in fact see gain and lasing. These systems have pretty low thresholds also, and this is buttressed by the fact that they have very large absorption cross sections because you have a lot of unit cells contributing to the transition. So they're exciting in that sense. But they raise kind of a conundrum from this transient X-ray diffraction measurement viewpoint. And one of the reasons they were interesting to look at is kind of from the following perspective. In that graph I showed you before, that was for Ked sulfide, so it's slight elaboration. These materials are really large in one direction, along their long axis here, essentially, where you might call that a large radius. That's a little bit of a stretch, but they have a large number of repeat units of the crystal in one direction, and then they can be really, really thin in the other direction. So they might be tens of nanometers in length, and they may only be 1.5 nanometers thick. So essentially, from the perspective of melting one of these things, what's important is that kind of the low, the shorter axis here, or shown as these planes cutting through the system here. You don't have a lot of repeat units, and that looks like not a lot of lattice enthalpy in this direction and kind of like curvature. Whereas in this other direction, you have repeat unit again and again and again along these 1,0,0 planes. And so maybe these materials are really robust. So can you see something like anisotropic disordering? And that might sound strange because you have this one particle, but essentially, can you lose diffraction intensity in one set of planes and kind of maintain it in the other? And so first off, there is anisotropy, and that's plain as day in X-ray diffraction, shown here for 3, 4, and 5 monolayer thicknesses, or they're really 3.5, 4.5, 5.5, because they're all cadmium terminated on both sides. But so for planes that cut through and look at both axes, kind of diagonals cutting through these systems, these diffraction patterns look pretty broad, right? And you might expect that because they're very, very thin. But in directions that have a component that is mainly looking along this direction, where you can put a lot of slices through this system in this direction, you get narrow diffraction peaks. And similarly up here at the 400, which is kind of advantageous to look at just because it's totally isolated. It's just looking at this one plane out here. These are also narrow in comparison to this guy, the 111. So can we in fact see that we have any kind of anisotropy if we now look at them in transient X-ray diffraction and try to compare them? And there's some interesting details of these systems, such as the tetragonal distortion, which I don't really get into here, but these line shapes for these intermediate, or for these other thicknesses here have some asymmetries and all that are real due to the fact that you get reconstructions of what the outermost layers look like of the system. Okay, so as a function of fluence, looking at X-ray diffraction of here the 5 monolayer, one thing I want to draw your attention to is for the 400, which is that set of planes where there's a lot of repeat units, which would suggest it should be stable. Looking at it as a function of fluence, at low fluences versus medium high, these things are very symmetric derivatives. Okay, and they also, you'll notice the derivatives are comparatively narrow relative to some of these other features, because it's essentially a larger crystal. You have more Fourier transform of repeat units of your unit cell. So these look very derivative-like. And at the highest fluences, you will see that they are somewhat asymmetric, right? The height of the positive becomes smaller than the height of the negative. So we eventually are disordering them. But if you look at some of these other features here, like the 220, where we're picking up, or sorry, let me draw your attention to 311. Like here, we have some contribution from the unit cell in every direction in real space. And so here you see very, from early fluences, this starts to become asymmetric negative early on. And it does have derivative component, but it's always outnumbered by the amount of negative going signal relative to like the 400. The same is observable in the 220 as well. So these signals are in fact suggestive that you have asymmetry in the amount of disordering in the crystal. There are additional complications in this system because of having that tetragonal distortion in something like the 220. But to summarize some of that, if you look at the gray shaded region, this is what you get if you difference just the statically heated sample. So if we just take the sample, no time resolved measurement, but just changing temperature of the sample, and then difference those patterns, you get this gray feature, which is just saying that as you heat the system up, this is what the thermal component only would look like. And instead, what we're seeing is this big negative going feature. So we do get anisotropic disordering of this system. And what it's essentially telling you is that in the 400, where you have all those repeat units, the crystal still looks sufficiently crystalline to diffract efficiently. But then when you start to look at these, especially these planes that are going out in where you have less thickness, less repeat units, it looks disordered. And so a picture that you might think about is if you have something like a piece of gum, which is kind of like what these things look like, you're making the gum waver up and down, kind of like pushing it together or something like that. Whereas if you look along the length of the gum, it still looks like the same width, and the atoms are still on registry in that direction as you move along it. But now these planes here are getting ruined when you start to have that waver up and down. So you might call that wiggling or wriggling or something like that. And it is in fact losing crystallinity in that direction. These systems also start to show hints of 2 recovery timescales, which is kind of unexpected. So this ultimately, just to summarize it quickly, is that the recovery scales of these systems are going to be dominated by diffusive behavior. So the exact mechanism of it is something we still try to understand. But in the 0-dimensional particles, remember that the smallest crystals recovered the fastest, and then bigger ones took longer. And that's really just because you have heat leaving the system, trying to get into the solvent. But if you're leaving from a bigger object to start with, it's harder to randomly walk away and leave the big system. Whereas if you have a tiny little particle and the heat leaves it out into solvent, the chance of the heat essentially ever coming back is really, really small. So the recovery looks faster. And these systems also have these different dimensions. So if you're having heat leave from a large face of the unit of the crystal versus from a smaller face of it, that's something that can overall dominate what this recovery looks like. The crystallinity recovery is also something that looks asymmetric in that sense of it taking a long time for these wiggled phases to go away. We've started to see some hints in other systems of dependence on what the ligand is on the surface of the particle. So in copper indium selenide, we've looked at this system mainly as a way to get to solar cells and the additive manufacturing processes related to making bulk solids. A fairly quick synopsis of this type of data is that it looks a lot like Ked Sonic zero-dimensional nanoparticles, where a key development that is of interest there, though, is that in these systems, we can either have oleolamine on the surface, which is a big alkane chain, or we can go to some of the most compact ligands possible of like S2 minus. So, and there is a solvent change going from an organic to a more polar organic, sorry, non-polar organic to a more polar organic of DMF versus like toluene or octadecene for oleolamine capped particles. But what you see here is that in these recovery timescales of watching disorder go away, which is suggestive of losing thermal energy, the S2 minus case is recovering appreciably faster than the oleolamine capped particles. And these are the exact same particles, just having been surface exchanged post-synthesis and then still having the same optical properties, suggestive that they're not modified like etching or something like that. So that starts to get into this question of what's called interfacial thermal conductance. So this is the idea of if you have something like a sphere, like a metal sphere that's hot, or some insulating sphere that's hot, if you say plunge it into water, you might be limited by just how fast can phonons hit the surface and leave the particle, or do they ever bounce back and stay in the particle? So do you have trouble getting out through that surface, or are you more limited by diffusion away from it and so forth? So that is captured by a value called G, which is in megawatts per meter squared Kelvin. And the upshot of this is that if you start to think about interfacial conductances, that's what these recovery timescales are starting to get measures of. But it's always done with these cases of these X-ray experiments where we don't have infinite signal to noise and so forth. So we'd like to do this with higher signal to noise, but do you see these appreciable changes in what interfacial thermal conductance looks like, which might be something you could expect based on how different in length these ligands even are. So you can think of the oleolamine as like wearing a fur coat, and the heat has more trouble getting out, whereas this is your Hawaiian shirt just barely sitting on the surface, and heat can get through it and get out more quickly. So the last part I'll try to tell you about is not using X-ray diffraction, but trying to get more at that interfacial thermal conductance type of problem. And this is something a number of people in the field have worked on and given a lot of thought to. And it goes back to those questions of intraband relaxation, of if you have a hot electron and it drops to the band edge, do you create a bunch of thermal energy in the core, and then that energy has to leave the core and go out? And our transient X-ray experiments essentially say, yes, that's pretty much what happens, because we can see the core atoms diffracting differently. But there's this other type of question of, if you have a hot electron and it drops down in energy, that difference in energy here might be really closely resonant with a vibration of the ligand. So maybe instead of ever creating heat in the core, you just create some heat in the ligands. And our X-ray experiments aren't sensitive to that. But these experiments generally trying to look at this electronic vibrational energy transfer process are really hard, because most ligands don't really show you much of a thermal signature of being hot. So I'll skip over the part involving perovskites that kind of primed us to how to do this. So I'll just go through it really briefly, which is we started actually not with a nanoparticle to get to this method of doing this experiment, where we were looking at things like methylammonium lead iodide bulk, trying to think of how can we see excitations of the vibrations of the methylamine component in it. And it turns out that's quite temperature sensitive. So we went about doing optical experiments, watching it just versus temperature, calculating differences that are present, and then trying to look for them in transient optical experiments. So transient mid-infrared, trying to look for thermal population of that methylamine component. And in fact, we can see that. But in this experiment, it's still electronic excitation of the semiconductor, and you're creating some heat and just watching it equilibrate. And it was remarkable that the methylamine takes a long time to thermally equilibrate with the rest of the lattice. But we still didn't really know where the thermal energy was, and we didn't set it off in the direction that we necessarily wanted. So that's when we started to turn around this measurement and think about, well, you have this band gap that's really sensitive to temperature, and this material's band gap changes around 145 Kelvin due to phase transition. So we could do something like sit down here at low temperature or sit up here at higher temperatures and photoexcite in the mid-infrared to heat the organic, and then see if we can see the rest of the lattice equilibrate by watching the band gap change. So that's something that we had set about doing, and you can pump it 3100 wave numbers, which is exciting organic components only, and then watch the band gap in the electronic spectroscopy change over time. And that's something that evolves pretty slowly in perovskite. But turning our attention to nanoparticles, you can take something like, say, a Ked Sonic Nanoplatelet, which has a band gap that's quite temperature sensitive, called the Vargian relationship again, where phonons are populating the system. It's making the system, the lattice expand. The expanded lattice has a band gap that is different than the cold lattice. So if we now take that EVET type process and look at it in a different direction, we can photoexcite the ligands in the mid-infrared, have a nanoparticle here, and we just watch it with a probe beam in transient absorption to see, is it getting hot or not? And manifestations of it getting hot would be that we see differences that look something similar to differences in static spectroscopy versus temperature. And so lo and behold, that works. So this is something where these experiments are kind of cute, because when you first photoexcite at time 0, which if you've done transient absorption, usually your biggest signals are right around time 0. These signals at time 0 are 0 because nothing happens initially. You heat up organics by creating a CH stretch, and we don't locally excite it. You randomly excite the CH stretch because they're localized types of vibrations. But then over time, you start to see that thermal energy move into the nanoparticle by processes we're still trying to fully understand. But you can see it doesn't happen just instantly. It takes tens of picoseconds. And so that's something that is starting to tell us about interfacial conductance of these systems. So we can take small nanoplatelets or quantum dots or core shells, and these things all influence what the lifetime is of that thermal energy transfer. And it's on this tens of picosecond type timescale, which relative to the EVET process is a different initial and final set of states, but it's something that also starts to point to ways to understand EVET. But also you can look at the recovery timescales of these systems and try to get a sense of, once the thermal energy has gone in, then you can also watch the thermal energy go back out. And that's something now that's comparable with our transient X-ray diffraction. And so the upshot of this is that if you have particles in solution, you see recoveries that are fairly quick. And the timescales of, if you fit this is something like 300 picoseconds or something like that, but depends on the solvent. And that's something that is comparable to what we see in these X-ray diffraction experiments, that these recovery timescales relate to the energy flowing out. And if you have a solid, it gets much slower. And that's something we're trying to understand better. But you might expect that you don't have diffusion of solvent, and that's something that slows down the process. Furthermore, getting back to the beginning of this, we can do those types of experiments where we have cold Ked Sonic nanoparticles that we photoexcited and tried to argue that fast emission was related to thermal excitations of them. And now we can just directly do that. We can photoexcite the system. We see this burst of emission that we thought was due to phonons helping triplet states emit. Come back in later with a mid-infrared excitation, photoexcite it. That thermal energy moves into the nanoparticle, and then we get bursts of emission. So your population didn't increase because you're pumping in the mid-infrared. So the only thing that could be changing is the oscillator strength. Okay, so that's what I wanted to show you guys today. So mostly I was talking about transient physical probes. I didn't cover all of them. We do other things like transient stimulated Raman, but we can see things like lattice expansion and transient disordering, crystal phase transitions, and season wet bromide. We think this is something that's relevant to operation of devices, especially gain and lasing, but it's relevant too to still lower fluence applications. I showed you that nanoplatelets have anisotropic disordering. That's something that we're still trying to understand more in other systems as well. That ligands can actually impact interfacial thermal conductivity, which is maybe not a shock, but it's something that there's data on. And then showed you some with selective excitation of ligands and trying to get a sense of these thermal interfacial conductances better through these really directed excitations. So thank you very much. I'm happy to take any questions.